Jai Hind students, myself Dr. Pankaj Goel, Assistant Professor in Ajay Kumar Garg Engineering College. Today I am going to deliver a lecture on a very important topic, that is the generation and detection of double sideband suppressed carrier technique. As we know that the amplitude modulation technique that we use to transmit the information from one point to another carry three components, and these three components are known as carrier, lower sideband and upper sideband. Now, out of these three components, we know that the carrier does not carry any information. It is just used to carry the information signal. The information is contained in the sidebands, and if in this transmitted signal we have to save the power, then we have an option to suppress this carrier signal to a great extent. We can only transmit the sidebands which carry the information, and at the receiver end we can demodulate the sidebands into the original modulating signal format. So, today we are going to discuss it. So, the advantage of using double sideband suppressed carrier technique is that this technique is power efficient. It consumes low power, because in our amplitude modulation technique we know that out of the total power that is transmitted, minimum two third of the power is taken by the carrier, and that carrier does not carry any information. So, if we suppress the carrier and only transmit the sidebands, then we save 2/3 of the power. So, that is a huge power that we can save by using this technique, double sideband suppressed carrier technique. But that saving in power does not come for free. There is a certain complexity in the hardware at the receiver end that is required if we use double sideband suppressed carrier technique. That is, if we suppress the carrier and only transmit the sidebands, then at the receiver end to get the message signal back, we need a more complex circuitry. So, that is the drawback. Now, as we know that our carrier signal is denoted by AC cos omega ct, where omega c is the angular frequency and AC is the maximum amplitude, and the modulating signal is denoted by here AM cos omega mt, where AM is the maximum amplitude of the modulating signal, and omega m is equal to 2 pi fm, where fm is the modulating signal frequency. Now, if we have to obtain the double sideband suppressed carrier wave, then it can be obtained by doing the product of these two signals, that is the carrier signal and the modulating signal. So, we can see here that if we do the product of the carrier signal and the modulating signal, then we, by this formula for cos A cos B equal to cos A plus B plus cos A minus B whole divided by 2. So, from here we get the upper sideband and lower sideband, which have frequency of omega c plus omega m and omega c minus omega m, and there is no carrier here. We will see the complete circuit after 2 slides. Now, here we can see that if we obtain the double sideband suppressed carrier signal by doing the product of modulating signal and the carrier signal, then this double sideband suppressed carrier signal, which is basically consisting of only 2 sidebands, upper sideband and lower sideband, and the frequencies are Fc plus Fm and Fc minus Fm. So, the frequency spectrum for this double sideband suppressed carrier signal can be represented as, where we can see that there are two sidebands, one range from Fc to Fc plus Fm and the other range from Fc minus Fm to Fc. So this is our lower sideband and this is our upper sideband. So these are the frequency spectrum for lower sideband and upper sideband. Now, all the transmitted power in this case is contained in the two sidebands and no carrier is present. And the bandwidth of double sideband suppressed carrier signal is twice the modulating signal bandwidth, that is, the bandwidth is 2 FM. Now we'll see the circuit for generation of double sideband suppressed carrier. See, here we have a modulating signal, we have a carrier signal, and we know that the product of these two will get us the double sideband suppressed carrier output, which consists of, and the output is expressed as two components, the upper sideband and lower sideband, Fc plus Fm and Fc minus Fm. Okay, so these are the frequency of the two components, upper sideband and lower sideband, and this together is denoted as double sideband suppressed carrier wave. Now we'll, in the next slide, we'll see the block diagram for generation of Dsbsc technique. So this is a balanced modulator circuit. Here we can see that this is our message signal SMT. Now this message signal is given to two modulators, two amplitude modulators, AM modulator 1 and AM modulator 2, and note that in the first AM modulator the modulating signal is given as it is, whereas in the second AM modulator the modulating signal is shifted by 180 degree and then it is transmitted, then it is fed to the AM modulator 2. So it is 180 degree phase shift. We can see here 180 degree phase shift. Now to these AM modulator, the second signal that is given is the carrier signal, and the carrier signal that is given to the two modulators is in the same phase. Okay. The output of first modulator, first AM modulator is denoted by S1T and the output of second modulator is denoted by S2T. Here we can see that the mathematical expression for S1T and S2T here. Here we can see the difference between the two. This is the expression for amplitude modulated wave. Okay, and here the difference between S1T and S2T is the difference of this sign because of the 180 degree phase shift, that modulating signal by 180 degree phase shift is fed to the amplitude modulator 2. So here we are having negative sign and in S1T we have a positive sign. So these are the two signals that we obtain at the output of modulator 1 and modulator 2, S1T and S2T. Now we obtain the final double sideband suppressed carrier signal denoted by ST by doing the subtraction of S1T and S2T. So if we do subtraction of S1T and S2T, that is S1T minus S2T, we obtain the double sideband suppressed carrier signal. Here we can see that we are only left with the product of modulating signal and carrier signal, and the product of these two signals will give us the two sidebands, upper sideband and lower sideband. That we know that the product of these two signals will give us the two sidebands, upper sideband and lower sideband. by this formula for cos A cos B, which gives us cos A plus B plus cos A minus B. So, we obtain the two side bands. So, this is the balance modulator circuit which is used for generation of double sideband suppress carrier signal. And as I just told you that the advantage of Dsbsc technique is that the output consume less power as compared to AM wave. Now, after generation of the double sideband suppress carrier, let us discuss the demodulation technique, which is also known as detection of the message signal. Now, as in case of double sideband suppress carrier technique, carrier is not present at the receiver end, because from the transmitter end we have not sent the carrier. So, at the receiver end carrier is not present. So, in the absence of carrier, when we are trying to obtain the message signal from the sidebands, we need a synchronous carrier signal at the receiver. In the absence of synchronization, we have certain issues which may lead to distorted output. Now, let us see. This is our double sideband suppress carrier signal ST, and here we have a local oscillator at the receiver end which is generating this signal cos omega Ct. That is this is the carrier frequency, and the output of these two is denoted by Vt, which when passed through the low pass filter, this is our low pass filter. When passed through low pass filter, will give us the final output V0t, which is our message signal. Now, let us see how the absence of synchronization between the local oscillator at the receiver end led to distorted output. Now, let us see this mathematically. This is the Vt signal. This is our Dsbsc signal, and this is our carrier signal, local carrier signal. Now, let us see, when we express the ST signal mathematically, we get this 2m AC cos omega mt into cos omega Ct, and this is whole multiplied by product of cos omega Ct, and we can represent it like this: cos omega mt and cos square omega Ct. Here cos omega Ct and cos omega Ct will be cos square omega Ct, and cos square omega Ct can further be expressed like this: 1 plus cos 2 omega Ct divided by 2. Okay, this part can be expressed like this. Now, when we open up the bracket, we are having two signals. One is AM cos omega mt, and the second one is AM and the product of this cos omega mt into cos 2 omega Ct. Now, we know that this part is our message signal, message or modulating signal, which we desire at the receiver end. So this product term, high frequency term, this is high frequency term, this high frequency term can be removed by using a low pass filter. What low pass filter does is, it pass a low frequency signal and stop high frequency signal. So this high frequency term will be stopped by this low pass filter and only the message signal is passed. So at the output of this low pass filter, we get our message signal. And this message signal is SMT. Okay. Now let us see what the problem is encountered at the receiver end in the absence of synchronization. This is the output in ideal case when there is no synchronization issue. Okay, this is our local oscillator frequency and this is our double sideband. So in the absence of any synchronization problem, we get the ideal output. But what happens when there is synchronization issue? Let us see. See, this is our double sideband suppressed carrier signal, which is basically the product of message signal and carrier signal. And if this carrier signal has a angle theta, where this theta is unknown to the receiver, then what happens? This is our double sideband signal and this is our local oscillator. And now this local oscillator does not know about theta. So because there is no synchronization, so the oscillator at the receiver end doesn't know about this variation theta. Now what happened due to this theta? Let us see. When we are going to do the product of these two signals, we are having theta. This is a high frequency signal which is removed using low pass filter and we are left with this part. The output of low pass filter is this. Now as we can see, the output of low pass filter consists of this message signal and this additional component cos theta. Now what can happen due to this cos theta? If we say the value of theta is 0, then we know cos 0 is 1, so there is no distortion. But in an extreme case, say theta is pi by 2, then what will happen? If theta is pi by 2, then what will happen? It will give us to 0 or no output, because cos pi by 2 will give us 0 and 0 multiplied by anything will give you 0. So if cos theta is 0, total output will be 0. So that is the synchronization issue. If the local oscillator at the receiver end is not synchronized with the transmitted signal, then due to this unknown factor theta, the output is not as desired. In an ideal case, if there is no distortion, then there is no defect at the output, but in case of there is a variation, there is a synchronization issue, the output is either suppressed or totally it may be 0 in the worst case. Now, this issue that we discussed is known as lack of phase synchronization. Now, similarly, let us see what happens due to lack of frequency synchronization. In this case, let us consider the case that local oscillator is not stable at Fc, but the local oscillator frequency is Fc plus del f. Okay, because there is no synchronization. So, if there is a frequency mismatch between the transmitted signal and the frequency generated by the local oscillator, there may be frequency mismatch due to various factors, because we do not have any mechanism to synchronize, and in the absence of synchronization, if there is a variation in frequency, maybe small variation, but if there is a variation in frequency and this variation in frequency is denoted here by del f, del omega. Now, what will happen, that this factor will come at the output. Okay, and again the value of this factor cos del omega t will decide the output. That is, due to these problems, due to lack of phase and frequency synchronization, we need to have a synchronization circuitry at the receiver end. Now, this is our synchronizer circuitry at the receiver end that is required to ensure that the output obtained at the receiver, that is the message signal that is obtained at the receiver, is distortion free. In the absence of this circuitry, there may be distortion. So, now let us study this circuitry. Here, this block diagram of this synchronization circuitry consists of 4 components, 4 modules. This is a square circuit which will give you S square T. This is our PLL phase lock loop which is used to synchronize. This is our band pass filter, BPF is band pass filter, and this is frequency divider by 2. And this complete circuit is known as a synchronizer. Here let us see, this squarer circuit will give you this signal which is expressed as S square T equal to AC square AM square cos square omega MT into cos square omega CT, and when we simplify it, we can express this term as this and this term as this. Cos, it is 1 plus cos 2 omega MT and 1 plus cos 2 omega CT. Now, upon further simplification, we get it 1 plus cos 2 omega MT plus cos 2 omega CT plus cos 2 omega MT into cos 2 omega CT. So, here we are having 5 terms. There are 5 terms here in this expression, as we can see, and out of these 5 terms, we only pass this term by the band pass filter and we suppress the remaining one. So, this is the output of band pass filter, AC square AM square by 4 cos 2 omega CT. This is the output of band pass filter. Now, the output of frequency divider is K cos omega CT, where the frequency is divided by 2. Here we have a frequency of 2fc, and here we have a frequency of fc. So this frequency divider circuit, this is your frequency divider circuit. It divide the frequency by 2. So we are having a frequency component which is k into cos omega ct, where k is a constant of proportionality. And this carrier frequency signal at the receiver end is derived. This is the carrier signal at receiver, and this carrier signal at the receiver is obtained from this Dsbsc, which is transmitted by the transmitter. So this carrier signal at the receiver, when we have obtained it from the Dsbsc, will always be in synchronization with the carrier signal which is transmitted by the, which is used at the transmitter. So if we use this circuitry in our circuit at the receiver end, there will be no synchronization issue and the output will be distortionless or distortion free. So we can see the drawback of this system, coherent or synchronization system, is that the frequency and phase of the local oscillator must be very precise, which is difficult to achieve, and it require, to overcome it, it require additional circuitry, and due to that its cost is high. So as we know that we have discussed that the advantage of Dsbsc technique is that the power consumed by the transmitter to transmit a signal is less. We save minimum 2/3 of the power if we suppress the carrier at the transmitter end. That is a saving at the transmitter end. We save 2/3 of the power minimum. But at the receiver end, the drawback is the cost of the receiver circuit goes high. So this is the trade-off. So this is suited for point-to-point communication, where we are having one transmitter and one receiver. Okay. Whereas the conventional amplitude modulated technique is used in broadcasting, where there is one transmitter and many receivers. Thank you very much.